Good morning to all of you. I welcomes to all in our lecture series on quantum mechanics. In our last two classes we are discussing on the topic that is quantum mechanical scattering and tunneling by one-dimensional potential step. So in our last two classes we have been in last class in part 2 of this topic I given a classical model from which one can be clearly understand what is the meaning of the potential step and when the flux of particle is going to be interact with this potential step, what will be the behavior. And in our last two classes we have been completed the first case, that is when kinetic energy of the incident flux of particle is greater than that of the potential or the repulsive force. If kinetic energy is going to be greater than that of this potential or the so-called you can say that it is a repulsive force or a step, then part of it will be reflected, part of it will be transmitted. Okay, so part of it will be reflected or scattered towards back, and part of is going to be tunneled inside this potential step. And what are the conclusions we are going to get, that also we have been discussed in our last class. So I suggest to all of you that you go through that two videos, part 1 and part 2 of this topic. And in this video we are going to discuss second case, that when the kinetic energy of the particle, that means E less than V0, that means if the kinetic energy of this particles flux, the kinetic energy of this flux is going to be less than that of the potential, then what will be the behavior of the particle at the boundary or at this interface of this step. So let's start to discuss. Okay, that is nothing but is your case 2. Case 2, when the kinetic energy, here E means fully kinetic energy is less than that of the potential. So here the same thing it has been written, that suppose uniform beam, or you can write flux of particle, uniform beam of particle or flux of particle each mass m and kinetic energy, purely kinetic energy, and traveling along positive x-axis direction, that means from minus infinity to towards positive x-axis direction, originated from the minus infinity, then beam encountered or the flux encountered at the step at the origin x is equal to 0 is shown in the figure 3. Now consider psi 1 x and psi 2 x are the wave functions for the motion of the particles in the region 1 and region 2 respectively. So let psi 1 and psi 2 be the wave functions of the particle in region 1 and region 2. Okay, so as we know that quantum mechanical particle, if in the dynamics, so they have to obey the Schrodinger equation. So now if we are going to set the Schrodinger equation, time independent Schrodinger equation for region 1, then what we are going to write? As we have the potential step in the region 1, the potential is V x equal to 0. That means here the kinetic energy is not going to be interact with any type of force in region 1, means the particles is freely moving in this region, but exactly at x is equal to 0 and onwards they are interacting with a potential, or you can just imagine a repulsive force. Suddenly a repulsive force, they have been perceived, means the particle flux are going to be perceived at x is equal to 0. So only for that we have considered that psi 2x, that means behavior of the particle will be different as compared with this one. That means here the particle have fully kinetic energy. Total energy means purely kinetic energy, but in this region the particle have kinetic energy and potential energy. So if in this section we are discussing E is less than V0, means whatever the kinetic energy particle have, that is not enough or less than that of the potential which is situated at x is equal to 0 to onwards up to infinite. Okay, so as we defined that psi 1 is the wave function for the region 1, then time independent Schrodinger equation for region 1 where potential Vx is equal to 0, then the time independent Schrodinger equation will be d square psi 1 by dx square plus 2m by h cross square E minus Vx. Here Vx equal to 0, psi 1 equal to 0, let this is equation number 1. And if we are going to consider k square equal to 2m E by h cross square, then this will be written as d square psi 1 by dx square plus k square psi 1 equal to 0. Let this equation number is 2. Now in case of region 2, if we are going to consider, in case of in this case here E is less than V0, and in region 2 the potential Vx equal to V0. In this region you just write in bracket Vx equal to V0. Okay, so for this region what will be the time independent Schrodinger equation? In general we can write this one, del square psi 2 dx square by dx square plus 2m by h cross square E minus V0 psi 2 equal to 0. In general we can write this one, but here the condition is that E less than that of the V0. So only for that it will be d square psi 2 by dx square minus 2m by h cross square V minus E0 psi 2 equal to 0. How it is, I am going to show you. See, suppose here it is given that, see, E is less than V0. Okay, let E equal to 5, let E equal to 5 and V0 equal to 7. Let E equal to 5 and V0 equal to 7. So now if I am going to write E minus V0, that will be 5 minus 7 and answer will be minus 2, right? 5 minus 7, answer will be minus 2. Now instead of writing E minus V0, if I am going to write minus V0 minus E, the same answer I am going to get. See, minus 7 minus 5 also minus 2. So instead of writing E minus V0 plus E minus V0, here we written minus V0 minus E, psi 2 equal to 0. Okay, now let beta square, this is beta square, not B, beta square equal to 2m by h cross square V0 minus E. So hence it will be d square psi 2 by dx square minus beta square psi 2 equal to 0. So here this equation, these equation number 2 and 3 are two second order differential equations. So the solutions of equation number 2 and 3 will be here written. Now the general solutions of the equation number 2 and 3 will be how much? For region 1 the wave function psi 1x will be the solution or the general solution, because it is written in the d square psi 1 by dx square, here d square psi 2 by dx square, but here it is plus k square, here minus k square, minus beta square. Okay, minus beta square. Here the two roots will be plus or minus ik, but here the two roots will be plus or minus beta. Got it? You can see that here if you are going to find out the root, this will be m square plus k square equal to 0. So m equal to plus or minus ik. Here m square minus beta square equal to 0, m equal to plus or minus beta. That we have been already studied many times in our differential equation chapters. So the general solution of this differential equation will be linear combination of these two solutions, and linear combination of two solutions also here will be considered. So the general solution of the differential equation 2 and 3, equation 2 and 3 will be psi 1x equal to a e to the ikx plus b e to the minus ikx. Let it is equation number 4. Psi 2x will be equal to c e to the beta x plus d e to the minus beta x. Let it is equation number 5. So here a e to the ix is represents the wave function of incident wave of amplitude a traveling along positive x-axis direction, along the positive x-axis direction. Okay. B e to the minus ikx represents the wave function of reflected wave of amplitude b traveling along negative x-axis direction. This is called as a reflected wave. One is incident. See, this is the scenario. This is the particle flux moving and it is interacting at this interface. So this is represent the incident and this is represents the reflected. Okay, and c e to the beta x, one exponentially increasing wave function which is non-oscillating. See, here there is no imaginary term is there, so it is not a oscillating. It is only exponential increasing function along positive x-axis direction. And here see d e to the minus beta x, exponential decreasing wave function which is non-oscillating along positive x-axis direction. So see here c e to the beta x means in region 2. Here you just add it in region 2 bracket in region 2. So this is these two things, incident and reflection, obviously in region 1, and these two things, two wave functions, so c e to the beta x, c d e to the minus beta x, observed in region 2 and region 2. One is exponentially increases, one another is exponentially decreases. So as per the boundary condition, we know that if x tends to infinite, the wave function should have to be 0. So if we are going to consider this will be the wave function exist in this region, then it will be not validated, because if we are going to put x equal to infinite, this term, whole term will be infinite, will be not obey the boundary condition. So this wave function is not going to be considered. This exponentially increasing wave function is not going to be considered in the region 2. But here exponentially decreases function is there, which is decreasing continuously along positive x-axis direction. So one is like this, another is like this. So if we are going to consider plus infinitive or at infinite, see at infinite, so it will be e to the minus infinity, will be 0. So at infinite psi is going to be 0. So this will be acceptable, this could not be acceptable. Hence psi 2, whatever we got the general solution from the differential equation, differential equation 3, the first term, exponentially increasing term, could not be acceptable, because if we are going to accept this one, this will be not obey the boundary condition, that is at x tends to infinite, psi should have to be, or wave function should have to be 0. This could not be acceptable because this not obey this boundary condition, but this obey boundary condition, that x tends to infinite, the wave function should have to be 0. So hence psi 2x finally will be what? It will be d to the beta x. The things whatever I have been discussed is written here. You pause the video and you can write. See, if we will consider c e to the beta x as a wave function, that I written whatever I discussed. Suppose we are going to consider c e to the beta x is our wave function, but for x tends to infinity, c e to the beta x is infinity. But according to boundary condition, a acceptable wave function has to follow that x tends to infinity, the wave function should be tends to 0, but it is not obeying that boundary condition. So hence c e to the beta x not acceptable. So finally psi 2x will be how much? Only d e to the minus beta x. Let it is equation number 6. Okay. see, whatever I am doing the things here, it is only for your explanations. Here you can draw a small figure, this one you can write, this is belongs to c to the beta x, this exponential decreasing things is d to the minus beta x. You can draw for you in your note, but in the exam point of view, this drawing is not required. So we found the wave function in region 1. The net wave function in region 1 is this one. The net wave function in region 2 is this one, which is represented by equation number 6 and equation number 4. Now the coefficients a, b and d can be evaluated by using the so-called boundary conditions. Okay. Now determination of amplitudes by boundary conditions. Put the heading. We have to consider the boundary condition one by one, and then easily we can evaluate the so-called amplitudes or the coefficients. The boundary condition for the wave function are wave functions. The boundary conditions for the wave functions are psi 1 at x is equal to 0 should be psi 2 at x is equal to 0. See here, this is the interface, means at x is equal to 0 the two regions are joined together. When the two regions, remember the so-called interface word means at the interface two different regions have to be joined together. So at x is equal to 0 is so-called interface which is joining region 1 and region 2. So at this interface we know that the wave function is travelling from this region 1 and interacted at the interface. So if there is a wave function possible in the region 2, there is a wave function suppose, then the wave function psi 1 has to be continuous at the boundary. So that means at that boundary at x is equal to 0 both the wave function is going to be same. Psi 1 at x is equal to 0 will be equal to psi 2 at x is equal to 0. So it is continuous means the first derivative or the so-called slope will be also same. So the first boundary condition, that is a equal to psi 1 at x is equal to 0 will be equal to psi 2 at x is equal to 0, that is wave function is continuous at the region, right? And the second boundary condition is d psi 1 by dx at x is equal to 0 equal to d psi 2 by dx at x is equal to 0. That means first derivative of the wave function is also continuous. Okay, using a and b for 4 and 6 we found. So now we are going to use this boundary condition for the equation 4 and 6. What is the 4? 4 is a e to the ikx plus b e to the minus ikx, and 6 is the representation of the wave function in the region 2. So now we are going to consider at x is equal to 0. If we are going to put x is equal to 0, it will be e to the 0 1 e to the 0 1 a plus b, and here the if we are going to put 0, it will be only d, because e to the 0 will be d. So what we got, a plus b equal to d. We got a plus b equal to d. Let it is equation number 7. Now we are going to consider the second one that is d psi 1 by dx at x equal to 0 is equal to d psi 2 by dx at x equal to 0. First you consider the first derivative of this one. First derivative of this one will be how much? First derivative of this one will be I k a e to the ikx plus minus I k b into e to the minus ikx I k a to the ikx minus I k, because it is minus ikx, so I k into b into e to the minus ikx. So at x is equal to 0 means it will be I k a minus I k b. I k, if we are going to take common, then a minus b, I k into a minus b for psi 1. Similarly psi 2 is how much? That is d e to the beta x. Psi 2 is how much? D e to the beta x is d e to the minus beta x, sorry, d e to the minus beta x. So its first derivative will be how much? Is first derivative minus beta d e to the minus beta x at x is equal to 0, it will be minus beta d only. Okay, psi 2 will be beta d. This will be this one. This will be this one. So same thing, it has been written that I k see ik a minus b equal to minus beta d, ik a minus b equal to minus beta d, let and a minus b equal to I beta by k, let this I beta by k into d, let this is equation number 8. This is d, okay, this is d. Now you have to add the equation number 7 and 8. Now add these both the equations, what we are going to get? If we are going to add these equations, then we are going to found 2a equal to d plus I beta by k into d. That is 2a equal to, if we are going to take common d, then it will be 1 plus I beta by k into d. That implies d equal to 2k by k plus I beta into a. Let it is equation number 9. Now put this value in equation number 7. What is equation number 7? Is a plus b equal to d. Now you have to put d value over here. This will be a plus b equal to 2k by k plus I beta into a. So it will be b will be how much? This a will be go this side will be minus. So take the a will be common. It will be 2k by k plus I beta minus 1. A is common. So if we are going to add this one, it will be b equal to k minus I beta by k plus I beta into a. Let it is equation number 10. So we found d equal to in the term of a and also b in the term of a. Okay. It is 2k by k plus I beta into a. It is k minus I beta by k plus I beta into a. Equation number 9 and equation number 10. Then further simplification, what we considered, let k is equal to r cos phi and beta equal to r sin phi. So k plus I beta if we are going to consider, then it will be r cos phi plus I sin phi, which will be nothing but r e to the I phi. Let it equal equation number 11. K minus I phi, similarly it will be r into the power minus I phi. Let it is equation number 12. Now by using equation number 10, 11, 12 in equation number 4. 10 is what? 10 is this one. 10, 11, 12. 11, 12 in equation number 4. What we are going to get? 4 means this one. 4 means our wave function, general wave function in region 1. That is this is. So here we are going to put the value of b first. That is a e to the ikx, as usually here written. Instead of b, we can write this one already we found here. B equal to k plus I beta by k minus I beta by k plus I beta into a. That much we have to put over here. It will be this much into e to the I minus ikx. Okay. K minus I beta, how much we got? R e to the power minus I phi. R e to the minus I phi divided by R e to the I phi, because k plus I beta is nothing but R e to the I phi. So R e to the I phi into a into e to the I minus ikx. So this will be a e to the ikx plus, if we are going to take here r got cancel. If this exponent plus will be moved to the numerator, it will be minus. So e to the power I phi into e to the power I phi minus I phi, e to the power I phi already is there. This will be moved to the numerator. Again it will be e to the power minus I phi. So it will be e to the power minus 2 I phi into a into e to the power ikx. Okay. Now you can take common a from these two terms. A bracket starts e to the power ikx plus e to the power minus 2 I phi into e to the power minus ikx, bracket closed. Now you have to take e to the power minus I phi common from these two terms. Then it will be a e to the power minus I phi. Here there is no e to the power I phi term. So if we are going to take common from this term e to the power minus I phi, so I have to multiply e to the power I phi, because e to the power I phi into e to the power minus I phi will be e to the 0 will be 1. Okay. So instead of 1, here it is 1 is there. So instead of 1, I can write e to the power I phi into e to the power minus I phi. So if I am going to take e to the power minus I phi common, only e to the power I phi will be there, plus here minus 2 I phi. 1 minus I phi is taken outside, so another will be written here, e to the minus I phi into e to the minus I kx, e to the minus I kx, bracket closed. Okay, so it will be a into e to the minus I phi in bracket, this will be add up I kx plus phi plus e to the minus I. So what we found that here e to the power I kx plus phi plus e to the minus I kx plus phi, phi plus kx or kx plus phi. So here multiply 2 and divide 2. So here e to the power I kx plus phi plus e to the power minus kx plus phi. This is nothing but cos kx plus phi. Okay, because this numerator is nothing but 2 cos kx plus phi, already 2 will be here, so it can be written as cos kx plus phi. Okay, so here psi 1 at last what we got, 2 into a into e to the power minus I phi into cos kx plus phi. Let this is equation number 13. See here I multiplied 2, divided 2. Instead of doing these things, this is simply is nothing but 2 cos kx plus phi. This is this much, means last expression. So this this line not required at all. This line not required, you just strike it, because this value is nothing but 2 cos kx plus phi is equation number 13. Okay, similarly using 9, 11, 12 in equation number 6, what we are going to get, 9, 11, 12. 9 means this one, d value, then 11 means this value, 12 means this one. We have to put in equation number 6. 6 means our wave function in region 2. This here means here we have to consider. So so the equation number 6 is nothing but psi 2 equal to d e to the minus beta x. So d value what we got, d value is nothing but 2k by k plus I beta into a. You just write 2k by k plus I beta into a into e to the minus beta into x. So here here 2 into k, what we defined here, k is nothing but r cos phi. So you just write 2 into, instead of k you have to write r cos phi, and k plus I beta, k plus I beta is nothing but r e to the I phi. You just write this one, r e to the I phi into a into e to the power minus beta x. Next r got cancelled, and we are going to get 2 into a into cos phi into e to the minus I phi into e to the minus beta x. Okay, simply nothing. Here 2 got cancelled, sorry, r got cancelled, and rest of the terms we have been written. That is nothing but final value of psi 2, means wave function in region 2. The solution psi 2, the solution psi 2, equation number 14. This is equation number 14, not 12. This is equation number 14. This is equation number 14, right? Or 12. 12, this is 13. This is 13, and so this is 14. So the solution or the so-called equation number 14 represents that wave function in region 2. Okay, resultant wave function in region 2 is exponentially damped up. See, if we are going to increase the x this side, this is exponential term is there, e to the minus beta x. So if we are going to increase x, this value is going to be decrease tends to 0. That means in region 2 this wave function is going to be decreased. That means not oscillatory, it is going to be decreasing. Okay, as shown in figure 4, but in region 1 it will be oscillatory, because psi 1 whatever we found, that cos kx plus phi, which is a oscillatory function. Okay, now psi 1 and psi 2 are shown in figure 4. The wave function is oscillatory in region 1. The wave function is oscillatory, where the particle can move when that means this is the region 1 represents the motion of the particle, that is maybe incident, that maybe and reflection both. If we are going to consider that the region is 1 is nothing but this R1 R2, region 1 is dynamics condition. So the wave function is oscillatory in region 1. Dynamics condition means a particle in dynamics, that means it is represent a wave function or oscillatory, we can say. So is oscillatory in region 1 where the particle can move, but in region 2 it is exponentially damped. Damped means decreasing and going to be 0, tends to be 0. That means particle cannot travel far into the region 2. Particle could not travel far into the region 2, but there is the probability of finding the particle up to some extent. That means it can be penetrate somewhat, it can be tunnel this barrier somewhat distance, but classically it is forbidden. Classically it is not possible. That you can go the last video number 2, I given one example classically, that one potential will be there if particle will be moving this side and the kinetic energy of the particle is less as compared to this potential, then it could not be penetrate at all. But here what we found, that means particle cannot travel far into the region, but up to some extent it can be travel. That means but there is non-zero probability finding the particle in the classical forbidden region. Classical forbidden region means with the help of classical mechanics it could not be explainable that why and how the particle is going to be found in this region, because the kinetic energy of the particle E is less than V0 here. How it has to be found here? But here we derived that there is some probability of finding the particle in region 2, but up to some extent. That is called as the so-called tunneling effect. Tunnel means penetrated. Okay, penetrated up to some extent. That is called tunneling. Okay, tunneling effect in classical region, even if E less than V0. But in classical, this is not acceptable. This is forbidden. This concept is forbidden, not acceptable in classical mechanics. So only for that it is written that, but there is non-zero probability also finding the particle in the classical forbidden region. Classical forbidden region means in this region will be called as classical forbidden region, but in quantum mechanics we found some extent of probability in this region. Okay, now we have to evaluate probability current densities. First we have to consider incident current density. So to evaluating the incident current density, we have to consider the incident wave function. The incident wave function is nothing but, the incident wave function psi in is nothing but a to the I kx. This is our incident wave function. So by considering incident wave function, we have to find out the incident current density, and the current density general expression is nothing but what? I h cross by 2m psi del psi star by del x minus psi star del psi by del x. So with a simple step omitting, I have been written over here, you just follow it. Okay, here we have wave function is a to the I kx. We have to just follow this expression for the finding the current density. So I h cross by 2m is here, I h cross by 2m here, psi del psi star by del x. Okay, psi del psi star by del x. Psi is how much? A to the I kx. A to the I kx del by del x of A to the I kx star minus psi star del by del x of psi. I written directly. Okay, so here I h cross by 2m, so A to the I kx into here A star, derivative of this one. Derivative of this one will be minus ik e to the minus ikx. See, star a e to the ikx star will be how much? It will a star e to the minus ikx, right? So derivative of this one, derivative of e to the power minus ikx, because this star, this complex conjugate of this one will be minus ikx, The derivative will be minus ik into e to the minus ikx minus psi star, it will be a star into e to the minus ikx into derivative of this one a e to the ikx will be equal to how much? Ik into a into e to the ikx. Okay, here it will be found that a star a mod square minus ik e to the ikx into e to the minus ikx, it will be add up, it will be 0, e to the 0 will be 1. Here a star a mod square ik will be here e to the minus ikx e to the plus ikx, that means e to the 0 will be 1. So we found that, and here what we found, here minus, here also minus, it will be 2 ik a mod square I and I square minus 1, already minus is there, so h cross k 2 got cancelled by m, h cross k by m a mod square incident current density. Now we are go for the reflected current density. So reflected current density, for finding the reflected current density, reflected wave function is how much? B e to the minus ikx. This is our reflected current density. By using this wave function, the reflected current density will be how much? Here initially we have to consider minus, because if incident current density is moving along this way, the reflected current density will be along this direction. So minus I by h cross by 2m, same formula, psi del by del x of psi star, psi stars because psi is this one, minus psi star into del by del x of psi. Okay, carefully you have to watch. Minus is there, I h cross by 2m into b e to the ikx, as usual I have been written here. The star of this one, complex conjugate, will be b star, it will be e to the plus ikx, the derivative of this one e to the plus ikx, because here is the star is there, complex conjugate of this one will be e to the plus ikx, the derivative will be plus ik into e to the ikx plus ikx minus b star e to the ikx, because this is the complex conjugate, complex psi star and del by del x of psi. Psi is this one, psi star means b star into e to the plus ikx. Okay, so e to the plus ikx into minus I k into b into e to the minus ikx. So similarly we can get h cross k by m b square, the net probability current density. This is our reflected current density. Previously we found the incident current density is how much? Is this one. The net current density will be how much? Ji minus Jr will be this much. Okay, but we know that b is equal to this one, so that b star, if we are going to consider b star, will be complex conjugate of this one, will be k plus I beta divided by k minus I beta into a star. The b star will be equal to a star. Here you just multiply b star. If we are going to multiply, then this will be this and this is going to be cancelled out, this and this is going to be cancelled out. A star is nothing but A star will be remaining, we are going to get. See, B star will be equal to this much into this much. So this got cancelled, this got cancelled, we found A star. That means B mod square equal to A mod square at last we found. Hence net current density in region 1 will be vanished. In this case, net current density will be 0. Current density. Okay. In region 2, the current density is how much? For this region 2, the current density can be found by considering the wave function, that is psi 2. That is only what we found, c e to the beta x minus beta x. Sorry, actually here we have been taken as d e to the minus beta x. So it is d e to the minus beta x, because in region 2 the wave function is d. So it will be d e to the minus, correct it, okay, correction you have to do it, d e to the minus beta x, d e to the minus beta x star minus d star e to the minus beta x del by del x of d e to the minus beta x. So by considering derivative of this one, we can found at last 0. That means in region 2 what we got, the current density will be 0. The current density will be 0. That means in region 1, why it is 0? That means how much incident, exactly that much reflected. So current density 0. In region 2, why it is 0? In region 2, why it will be 0? Because it is telling that there is no probability. Sorry, there is no penetration. Only for that it is found that it will be current density will be 0. Current density means here current density 0. That means the oscillation part is not to be considered. But probability of finding the particle in region 2 will be there. Carefully you have to listen it. Here we found in region 2 probability of finding of the particle will be there, but oscillation will be there. If there is no oscillation, no propagation, means what is the current will be there? Current means the particle has to be propagate. Here in region 2 there is no oscillatory motion or there is no directional motion of the particle. Only the amplitude of the particle or the intensity of the particle energy is going to be reduced and tends to 0. Okay, so if there is no motion, there is no dynamics in the region, then what we are going to get? We are going to get the current density, the so called dynamics or the current is 0. So that we got current density in region 2 will be 0. Next we have to consider reflectivity or reflectance or reflection coefficient, that is R is nothing but current density, reflection current density divided by incident current density will be how much? Will be 1. That is we found that B mod square equal to A mod square, and JR we found how much? H cross M, H cross K by M B mod square. JI we found H cross K by M A mod square previously, so R will be equal to 1. Transmittance or transmittivity or transmission coefficient, that is nothing but current density, transmission current density divided by incident current density. Transmission current density we found that is 0, so it is 0. Maybe it is disturbed, you not visualize perfectly. So this is nothing but reflectivity, reflectance or reflection coefficient is how much? Current density, reflection current density by incident current density. Reflection current density we found here how much? H cross K by M beta B mod square. Incident current density we found H cross K by M A mod square. If we are going to consider these things, these two values, then and also we found B mod square equal to A mod square, so it will be 1. And transmittance or transmittivity or transmission coefficient is nothing but current density, transmission current density by incident current density. Transmittance current density in region 2 we found 0, so it will be 0 by 0 equal to 0. Then means transmittance will be equal to 0. Okay. Now results and discussion, whatever we discussed, the summary I have been written in 4 points. You just watch. What in this case means E is less than V0. E is less than V0. It is found that all the beam are reflected back. All the beam means there is oscillatory part. Remember, beam means oscillatory part. All the oscillatory part reflected back. There is no probability current anywhere to the left of the potential step. Incident and reflection are equal, and to right the step it is also 0. The probability current is 0. The probability of the finding particle will be somewhat. Okay. The right of the step, RIGHT, right of the step, the wave function is non-zero but exponential damped up. Here see, one thing you have to perfectly, you have to carefully, you have to understand that here it is written that probability current means there is no oscillatory part in the region 2. There is no oscillatory part, but some particle can be found whose energy continuously decreases, that it is written here. the right of the step, the wave function. If wave function is there, the probability of finding the particle will be there. The wave function is non-zero but exponentially damped. Suddenly it will be damped. Damped means decreases. Suddenly it is decreases in this region. But there is no current. There is no oscillatory part in this region 2. So only for that we can say probability current in the region 2 is 0, and whatever the beam means oscillatory beam, flux, oscillatory part, whatever incidented on the step, all are reflected. We can say like this. Now we have to consider when V0 tends to 0. It is important discussion on this formula. In many exams questions are asked to you and you have to be answered. You just remember what I am going to discuss here. See, B0 when tends to infinity is finite. Suppose we have to consider the case V0 is infinite. V0 is infinite means whatever the potential step we considered, potential step value. Suppose this is the potential step and this is the particle is approaching, and this kinetic energy less than that is that its potential height. If this potential height will be increased infinitely, increase infinite as compared with the energy of the particle, then what will be happen? What will be the scenario? So that is the case. If V0 is infinite and E is finite, then what will be the scenario? Then beta will be infinite, because beta we know that from the initial you just check beta square is this much, beta will be root over of this much. So V0 if infinite, beta will be infinite obviously. So if V0 will be infinite, beta will be infinite. And B, the coefficient, this is the coefficient, okay. B will be how much? K minus beta by K plus K minus I beta by K plus I beta into A, and D 2K by K plus I beta into A, okay. So and limit B tends to infinite, that is B by A, limit beta tends to infinite, B by A will be how much? See, just see beta by A. Beta by A means it will K minus I beta by K plus I beta. This value is not required now. Only you just consider this one. And we are trying to find out beta by A. Beta by A when B by A. We are trying to find out B by A when beta tends to infinite. So B by A will be how much? K minus beta by K plus I beta. K minus I beta by K plus I beta. Now just divide K in each term. Then what we are going to get? See, you can divide beta in each term. What we are going to get? K by beta minus I. Here K by beta plus I. And for this case, beta is infinite, right? So K by beta will be 0. Here K by beta will be 0. So it will be minus I by plus I will be minus 1. So for this case, V0 or the potential value is infinite as compared with the energy. We found B by A will be equal to minus 1. B by A equal to minus 1. That means if B by A equal to minus 1, then B equal to minus A. That means B plus A equal to 0, which is nothing but the so-called amplitude of reflected wave, amplitude of incident wave, both are same but in opposite direction. Then we are going to get the standing wave and the net amplitude will be 0. I am going to show you. That means A is our what? Incident wave amplitude. So this is your incident wave amplitude. This is and B is your reflected wave amplitude, exactly equal and opposite. That means this will be the B. B amplitude. Both A equal to B but opposite with each other. Then what is the value we are going to get? You are going to get the 0. Okay. means the so called whatever we discussed here, the means current density, net current density in region 1 is going to be vanished. So at x is equal to 0, at x is equal to 0, what we are going to get? At x is equal to 0, the psi 1 will be equal to 0. Okay, because if a plus b equal to 0, at x is equal to 0, e to the power 0, e to the power 0 equal to 1, we are going to get psi 1 equal to a plus b, and here we got a plus b equal to 0. That means psi 1 will be equal to 0. Okay, and psi 2, if we are going to consider psi 2, at x is equal to 0, at x is equal to 0, beta already is infinite. So that means e to the power minus beta. Minus beta means minus infinite. That means it will be give value 0. Okay. So at x is equal to 0, both the wave function is going to be vanish. So at exactly interface here, if v0 is infinite, then at this interface both these two wave function is not going to be exist. So this is all about your step, potential step. We have explained in 3 parts, part 1, part 2, part 3, in 3 videos. I suggest to all of you that go through these 3 videos, and if any doubt you faced, you can ask me. We are going to be discuss. Thank you so much for watching this video. Thank you.